I'm just going to check code size. Fair enough, I think. It's good, right? Yeah. We won't be reading that too long anyway. So, hi everyone, my name's Azriel, and today I'm going to talk about building good UX for a command line application and using futures. The focus of this is not so much the command line application, but how you would structure your code using the asynchronous paradigm, and you can transfer the concepts over to a non-command line application as well. So, in the past, I worked in automation, and one of the things we used to do is we used to get programs to do human tasks really, really fast. So one of the tasks which I got given, which just last January, is to take a list of property titles, which come in some number and some names, and I'm meant to go to the internet and grab the address, phone number, and the last sale date of those properties. And sometimes you get some missing information for a title, and sometimes you get errors when you fetch those information back. So there were
where do you go on the internet?
The person I did this for works for real estate, so they've got access to the information. Most of it's public anyway. You just need to be registered as a real estate agent. Yeah.
Okay.
Yeah, and so yeah, we're not doing illegal stuff. Yeah, we don't just take people's information and then there you go.
Facebook. That looks like John Smith.
Yeah, it's on like New Zealand's public registry, I think, somewhere. Cool. So the minimum viable product to do something like this is there's some steps to access the information. You need to log in. You read the file which has the list of records, and for each record you go to the server, retrieve some information for it, and you dump it out. So a minimum viable product could look something like this. So this is not the real thing, it's just a simulation. So this is what you might see on screen. It works, it doesn't look very pretty. And sometimes if there's too many records, you might want to stop the process halfway. That's an interrupt. And so if you give this to a non-developer, or even if you give it to a developer, it's not good UX, even though it works, right? So what I wanted to do was to make a good UX CLI application. So something that looks more like this. Let's expand that. All right, so you can see I'm going to run this command, and there is a progress bar, which I'm going to pause right there. We've got 8 items. Progress bar goes 3 of 8. And if you look just up here, I interrupted it after it has done 3 records. After the interrupt, you can see that it's given me a report with 3 records processed with missing information, and then, that's all. When I run the command again, so here, it continues from point 3 onwards, which is important because if you've got 20,000 records that you're processing, and you've interrupted your process at like 10,000 records, you don't want to start at 0 again, which when you're doing automation, it's really tedious to wait like hours for it to get to the state that you were previously at. So this one goes on, and here we've got an error which happened on the 7th one. You can see that the error has this title number of a test error. That's my planted error to test error handling, and that's also interrupted. And if I run it again, it just continues from 7 and finishes. So that's the kind of user experience I want to provide in a command line application. And when you have a long-running application, you want to know the progress, right? So that's much better than the minimum viable product, where if you've got heaps of text scrolling across the screen, especially for a non-technical person, it's going to be much easier to know, to understand this progress bar. And you can skip these two. So the one thing I also wanted this to be was cross-platform, because one, I'm developing on Linux, but the user was on Windows. And you can see that over here, we've got a screenshot of it actually working. This is actually the real thing that he's using. It's got up to nearly 13,000 records, and he's left his computer on for like 13 hours. So it's about 1 hour per 1,000 records. So imagine like having to restart that when it crashed, right?
So you download it into a CSV, and then you continue that later on? Like, so if it crashes, you can recover that?
Yep.
Okay, the position.
Yeah, I need to have the input file separate from the output file, because I don't know how to edit in place. That's actually quite difficult to do. Yeah, if you think you're writing and reading from the same file, that's quite hard, right? Yeah. So that's the vision, and that's kind of like retrospect because it's implemented.
Well, MongoDB, they have a driver now. You could use Mongo as well.
So if we look at the steps to implement the quality product over the minimum viable product, so the minimum product has steps 1 to 6 on the left, and I've copied the steps exactly to the right. But around those steps, to add the extra quality handling in there, I have to handle interruptions. I need to read the output file before I start processing to know where I was before. I need to start a progress bar to give the user an indication of where we're up to in processing. And for each record, because I work in automation, I know that when you hit a server really, really quickly, it looks like a DOS attack, denial of service attack. So we don't want to look like an attacker. And actually, there was once his IP got banned because we hit one of the servers too quickly, but it got auto unbanned, so at least they don't perma-ban, right? Yeah, so we have to build rate limiting into our record information retrieval step. And after processing each record, we want to update the progress bar. So we increment it by 1 every time. And I do them concurrently, but not in parallel. We'll explain that. Because I need to maintain the order of records from the input file. And another thing is I stream the input file so that I don't read all of it into memory at once, so I'm not overloading the user's computer. Yeah, so all the best practices are encoded into this quality set of steps. And when we are interrupted by the interrupt handler up here, or we are done with processing all records, then we want to output the execution report. So when you hit interrupt, you don't just get blank blank line underneath your interrupt. Okay, so I know I said I was going to talk about asynchronously implementing this, but first I want to show you that it's possible to implement such a user interface synchronously. So no futures, no async. So the steps are actually as is, step 0 to 11 here. I've got this link. It's online to see the full source code, which implements the same user interface you saw. And I've got functions here marked with T0, 0, 0, 1, 2, 3, all the way up to 11 to map directly to the mentioned algorithm. And so you can follow the code and you can follow the steps up there to see that I'm actually implementing what I say I'm implementing. So you can implement a good user interface synchronously. And I'm going to show you, so this is a, give me that. Okay, it's not gonna. This is a stub application which behaves similarly to the real application, but I replace all of the web requests and the processing steps with just sleeps. So the CPU does nothing during that time. All right, so the synchronous implementation. Okay, so you can see that If I run it, it's got that nice interface. It's got the progress bar. It gives you the summary report at the end. The errors just is calculated based on some modulo of the number that you're processing. And I can show you that if I increase that to 1,000 records, it's going to go through all of them. So you get the nice user interface, just like the real application, and this is implemented synchronously. So given we can do this synchronously, why would you choose async, right? Why would you do stuff perhaps in a different programming paradigm if you can already do it in the one you understand? So in the async version, I've implemented the same thing asynchronously, and same algorithm, step 0 to 11. And yeah, warning, don't use this as a reference implementation. This is only for examples. You can see that I have an async function main and then the same steps, 0 to 3, 4, 10, and 11, 5, 6, 7, 8, 9. And then I've got something here which spawns tasks. So the async implementation is very much like the sync one. If we go to it, so here I'm a master, but it's the same. I can go to the async folder. If I run it, it seems to be slightly faster. If I run them together, I'm gonna give both of them 1,000 actually. Yeah, 1,000 things to process at the same time. We'll start the synchronous one up first, and we'll do the async one just then. And you can see that the async binary runs somehow faster than the synchronous binary. Cool. Any disputes over that? None. Good. All right. And if we look at the stats, the async implementation took 3 seconds. The synchronous implementation took 11 seconds. All right. So somehow it's like 66% faster, around there. And now let's go back here. Okay. So before we look at the async concepts, let's look at how we do fast food. So consider a fast food restaurant taking orders. You can choose your favorite fast food restaurant. They mostly do them the same. We've got a worker at the counter taking orders for a queue of customers. So if we were behaving synchronously, we would go to the first customer. Hi, how can I take your order? The customer gives me the order. I tell the kitchen, hey, I want to have this order made, and I will wait. And when the kitchen's done, I'll take the prepared order and give it back to the to the first customer, and I'll talk to the second customer. Hi, can I take your order? So, and repeat the same process. So if I did that, then I would be wasting time waiting, like doing nothing, while the kitchen's preparing the order for the first customer. So during that waiting time, I can already start handling the order, taking the request from the second customer, right? So let's look at the concepts of concurrency and parallelism. So reminder, concurrency is about making more efficient use of your existing resources to gain more productivity in your workflow. So workers can handle another customer's order while waiting for an earlier customer's order to be processed. So yeah, the key point is you're making more efficient use of your existing resources. And so if we look at this timeline here, the synchronous approach is when we take the order from the first customer, send it off to the kitchen, and we wait. And then when the kitchen's done, we return it to the customer and do the same for the second customer. The concurrent approach is to, when there's a gap, when there's a break between 2 steps for my first customer, I can use that gap to process the second customer's order. So I can start requesting what they want and then passing it off to the kitchen. And when I'm waiting for the second customer's order to be completed, I can revert to the first customer's order and return their processed order. And that way I've saved this much time. Cool. Any questions about this? None. Cool. Right, so parallelism. All right, so this is when we have multiple workers handling customers' orders. So here we gain productivity through using more resources, so more workers this time. So here we've got 2 workers, and they're both processing 1 customer each at the same time. So if you look at the time diagram, we can see that both customers start being processed at the same time, and both of them finish roughly at the same time. And you can notice that there is a gap here for both the workers. So in theory, if you've got 4 customers, you can handle them in parallel and concurrently at the same time. Cool. All right. So now I'm going to bring you through some concepts which map nicely to async concepts. So if you look at how a fast food restaurant operates, they actually implement async pretty well. Right, so to handle one request from one customer, you actually can break that request down into multiple tasks to be done before that customer's order is completed. So there is the task at the counter of receiving the order, passing the order to the kitchen to be processed, and then taking the processed order from the kitchen when it's ready and handing it back to the customer. So that's the kind of task at this stage. And in the kitchen, this guy, the task is to receive the order request from the counter, prepare the order, and then send it back to the counter. So you kind of got 2 interacting tasks over here. And we'll look at who does what. So normally in a restaurant or any other organization, you have some workers doing some task and other workers doing some other tasks. So some workers take orders, other workers process the orders. But we're going to try and shift our mindset to thinking of taking orders is one kind of work, processing orders is another kind of work, and available workers can do any available work. Got that? So the person who's over here can, at some given some decision, can switch over to processing orders on that side. And the person processing orders here might switch over to the counter by some sort of decision. Yeah. We won't go into how that decision comes about today because it's to do with executors. Yeah, and I'm not too familiar with that at this stage. Okay, so if we think of tasks as the thing that stays constant and workers can switch around, that model, worker A, so the person on the left, may take an order and send it for processing. Worker B may finish processing an order from the past and send it back to the counter. And worker A may switch over to the kitchen and receive the order that they sent in the first place from step 1. So they might send it over, but they might be the receiver of what they sent as well. Cool? All right. Okay, so task organization. So when different kinds of tasks exist, we have to organize them based on the resources they require. So over here on the left, I've got a stove with many stove tops, and on the right, I've got an ice cream machine. So I drew it like this because you can see that if there are multiple orders for, say, a burger, you can use one stovetop per order, and you can start each order concurrently. So I can start preparing one meal on the left, second meal on the right, while the first one is being prepared, and then third one in the middle. And so in the first method of task organization, which is a new task per request or new task per order, one person can turn on multiple stovetops. So that means I can process multiple things concurrently. At the same time, maybe a second worker can use the stovetops on the right. So I can process one set of orders, and then another person can process another set of orders in parallel. So in that model, the resource is shared and can be shared. And so in that, if you have a resource that can be shared, then the task that you create can be a new task per request that comes in. It'll become clearer when we explain the second one. So if we have a resource that cannot be shared, like the ice cream machine, if I have, say, 3 ice creams that I need to make, I can make one ice cream, but I cannot concurrently, after I started making the first one, I cannot start making a second ice cream at the same time. So you can see that the second machine requires that only one thing can be processed at a time. So this is when you have a resource which must be exclusively held. So if you're mapping it to Rust concepts, it's a mutable reference to something. So if you have a resource which must be mutably exclusively held, then the model for the task you want to use there is a long-lived task. And then you can have one worker who listens for requests to make ice cream, and since they have access to the ice cream machine, they can make the ice cream and send it back to whoever requested it through through some communication channel. So if you have a resource which must be exclusively held, you want to have 2 channels: one to receive requests and one to return the response. Or if it's a one-way channel, like just receiving requests and sending updates to a screen, then you just need that incoming channel. Okay, and we're going to look at this really briefly. So communicating between tasks. So given the previous 2 task organization methods, the new task per order or per request is a much simpler way of implementing asynchronous tasks. So that means if you can send all of the information you need to along with the task that you're creating, then you want to use that task organization method because it's much easier. Whereas if you have a long-lived task, you need to set up the communication channel, and that has a lot more boilerplate. We might look at code today if we have time, but there are examples of both of these inside the repositories. Okay, so we're going to, before we go to asynchronous design, any questions about those async concepts? None. Okay. Either everyone understood it or no one did, right? So let's go on. So to design your code to be fitting for an asynchronous, to design your code to be asynchronous, it's cleaner to design from scratch rather than migrating something. So you want to not really migrate an existing code base, because that way you're trying to organically shift bits of code to async, and that's not usually how synchronous code may be structured for. So we'll go through a few different steps on how you get a cleaner code base with an asynchronous design. One thing that is useful to do though is to try and do the rushed migration, which is to try and do the hackily switch everything from sync to async, because if you do that, you'll learn what the error messages are, and you'll learn how to recover. And it's useful to do that once, so when you see someone else trying to do that, you know how to do that as well. So the hack approach is to add async in front of your functions. So here's a function that retrieves information. You just add async function. You change your synchronous logic to asynchronous logic. So instead of a thread.sleep, which would explicitly tell the current thread to just do nothing for like 100 milliseconds, you use the asynchronous version of that, and usually that would come from the Tokyo library or the async standard library. And what that does is, when the thread has to sleep, it knows, all right, I'm going to sleep for however long, so during this period that I'm going to sleep, I'm going to do some other work. So that's why you would change from sync logic to async logic. You want to use types with asynchronous support. So for channels, if you use a synchronous channel, a receiver that's waiting on the message, let's say the channel has no messages in it yet. When you call receiver receive, it's going to wait and do nothing until a message comes in. Whereas an async channel, when you call receiver.receive, it's going to check if there's no messages, it's going to go off and do some other work, which is in your application. So it tries to make use of the current thread to do work as much as possible. Got that? Cool. And at this stage, Rust is pretty new in its async support. So you get error messages like this. So I expected some type X, and then I found some type X. So it's like, why do you complain? Right. The error messages are not as refined as the ones in the normal synchronous standard library. So yeah, if you are going to use async, you do need to be aware of that. And make sure you read the async book. It does tell you some of the error message strangeness that do appear, like I expected A and I got B, whereas A and B should have been swapped, that kind of thing.
Does adding async away to Rust, Rust application, does it come with a kind of a runtime? It must have come with some kind of runtime to kind of coordinate the...
Okay, so the Rust standard library contains the futures traits. So it contains the traits to implement if you want async types. But the actual executors for running your async logic are not in the standard library at this point. There's two bigger ones. One is Tokyo, and one is async standard. There might be more, but those are the two that I looked at. And so both of these have very high quality crates, and if you look at the documentation, it's very, very good. Yeah, so it's like standard library level.
So you need a crate
to run
async await.
Yeah. Yeah, but you don't need a crate to write async await code that compiles.
Yeah, but then will you be able to make use of async await?
So what you get back are types which have, so you get back a future type, and you can call poll on it yourself, that kind of thing.
Yeah. So you have to implement your own runtime if you want to do it that way.
Yeah.
Essentially. Okay.
Yeah, but Tokyo and async standard both come with runtimes. Yeah. And Tokyo is feature gated behind maybe 12 feature gates, so the runtime's really minimal. You only bring what you need. Yeah. Cool. So we're going to learn how to design a program for to execute asynchronously. So the first thing you want to do is to categorize your steps 0 through to 11 here from the scenario by the resources that they use. So we're trying to figure out what's the ice cream machine and what's the stove, that kind of thing in your application. So here I've got these 4 categories on the right, and the first one is kind of its own thing, handling interruptions. It's like a signal from the operating system. It's pretty much a listener for that interrupt from the user, or a sig kill, yeah. And for the processing category, there's reading the records from disk. There is reading the output records, the ones that I have previously processed from disk as well. There's augmenting the input records with the additional information, and that's writing it out to the output file. So all of that is kind of to do with reading and writing to the input and output files. So that's one category. For the web category, I need to have credentials to log into the servers. I need to have, I need to rate limit my requests. I need to authenticate with the server if necessary, and then I need to also retrieve information for each record that needs to be processed. And finally, on the right, we've got the reporting category. So the reporting category is showing that progress bar to the user. So starting it at the point where maybe I've already processed 5 records at the start, so I'll start at 5. I want to receive updates and update the progress bar on screen. And at the end, when the application is interrupted or it's done processing everything, I want to output the execution report. So these are categories that I've chosen for the steps. For every application, it might be a bit different. Some people might go even finer than this. So say your input and output files might be split into 2 different task categories. But in this case, I just kept it simple. Okay, so I'm going to actually duplicate this tab because we're going to look at the next one at the same time. Alright, so I got my categories on the left, and I've got this information flow on the right. So I've come up with this graph of order and information flow between tasks, and hopefully everyone can see that. So at the start, you can see that I've got some things that are only run once. So setting up the interrupt handler, reading credentials, streaming or preparing the property record stream, so on and so forth. Tasks 0 through 4. I'm actually going to do this synchronously in my application because it's done once. It's not much point making it concurrent or parallel. Whereas the heavy part would be this section when I'm streaming the records, retrieving the information from the web server, and then writing it out. So this would be the heavy part. And because I want my user interface to be responsive, I want this to also happen at the same time. But I don't want user interface freezing to cause my application processing to stop. Because everyone knows when you hit a button and the cursor spins, that's like not good UI. You want to have a responsive UI regardless of whether the processing is happening or not. So this task graph pretty much shows you that I'm going to have 4 asynchronous tasks which run at the same time. One of them is the listener for interruptions. One of them is this blue bit where I have when I'm reading and writing the records. There's this part where I'm retrieving the record information from the internet, because that can take time. And I've got the progress bar updates. So all of those I want to do asynchronously. So that's kind of what the first point talks about. I'm going to talk about the second point, so the dashed lines. So these dashed lines, between tasks, I need to somehow pass information from one task which is running here to another task which might be running there. And also for these ones, I've got interruptions which tell my progress bar to stop updating and output the report, or I've got my processing which is happening and it might finish, and that says, hey, update the progress bar and you're done. So I've got these communication lines between tasks. So if you remember the stovetop, which I have, which I can spawn a new task per request. That's what this line represents, because in the web request flow, I've got the ability to asynchronously create a task with a an immutable reference to the web client. So the web client will not mutate. I can create many instances that reference that same web client with the authentication details, and then I invoke it with web.retrieveinfo. So I'm passing in the record that I want to retrieve the information for, and then I await on it, and that would be in one iteration of the loop. And I can do that, say, 100 times or 1,000 times, depending on how many records there are to process. Any questions on this so far? None. Okay. All right. So channel send and receive. So this is when I have an ice cream machine. So the progress bar needs a mutable reference to self, because whenever I am updated, I need to keep track of the number of records I processed, and I increment the report that I've got by 1. So that's a mutable change, which means I need a mutable reference to myself. So this thing cannot be a, you can have multiple tasks which spawn against the same reporter. So what we have to do for this case is we have to have a receiver, which is the receiving end of a channel, and it's going to receive, so whenever this thing, whenever a record is processed, it's going to send a progress update to the progress bar or to the reporter, and then the progress receiver will check the process result, and when it's successful, I increment the successful count by 1. I can also have other messages like the retrieval went wrong and I increase the error count by 1, that kind of thing. So yeah, that's what those lines are. Cool. Any questions on this? No. All right. Let's go here. Okay, so comparison between synchronous and asynchronous applications. So the synchronous implementation is a simple network of complex tasks. So if I open this thing, you can see that it's generally got these 3 groupings. I have a startup phase, which has multiple tasks. Then I move on to the loop, which has multiple tasks as well. And then I do a reporting phase, which I output the report. So it's like 3 nodes with like multiple sub nodes within that grouping. Whereas the asynchronous model is a complex network of simple tasks. So I actually don't have lines around these, but the yellow thing's one grouping, the green thing's another grouping, the blue one's another, and the red one's another. So these tasks are grouped by the resources they access. And it's easier to know what will be affected if you change logic within one group. So like, it's easier to know what logic needs to change if your resource changes, because it's not going to affect logic in another group. So there's a trade-off between the two, but yeah, that's just for comparison. Effort for efficiency, so efficient use of your workers. In the synchronous model, you need to explicitly manage that. So if you know that one thread's going to be, or one operation is going to take a lot of time writing to I/O, you might instead spawn that I/O operation in a different thread, and you need to send the information maybe across the channel to that thread. So you don't have your, say, computation process blocked by I/O. So in the synchronous model, you need to explicitly code that. Whereas in the asynchronous model, it's naturally enforced by the code. It's naturally enforced because the implementation for asynchronous things is already encoded into the types that you use. So if you use synchronous types, you still get blocked, but you want to make sure you use asynchronous types. And the library availability for sync code right now, it's generally more available because we started with sync. Everything's going to be sync. Whereas for asynchronous code, async just got stabilized 2 months ago, I think. So what we've got for library support is quite minimal. The core stuff that you need, like channels, I/O, I think networking as well, it's all done in Tokyo, maybe MIO, and async standard. But for other manipulations, like I want to read a CSV asynchronously, or I want to serialize something, those are generally still only synchronous. And you can implement the async versions, but it's just not yet done for you. Okay, so review. So I'd like to point out that good UX can still be implemented with both sync and async paradigms. It's worth spending time to design an async application rather than migrating a synchronous design incrementally. And then Rust's async ecosystem is still early days, but it's promising. Cool. Any questions? Okay, cool.
In your example, were you using when you're downloading things from the web, is like every kind of step in the progress bar, is that one request?
It's actually like, so in the real application, it's more like 5 or 6 requests.
Okay. Yeah. And you do those
asynchronously
do you
as
do
well.
multiple at the same time, or?
So I do them at the same time for different records, but for one record it is still synchronous because one request's output is necessary for the input of the next request. Mm-hmm. Like I'm searching for the ID of this title, and then it's got a mapping ID, so I need to look up the mapping ID, and then when that request returns, then I can look up the next request. Yeah.
So how do you handle the rate limiting when you do the requests in parallel?
Okay, so in the real app, there is I actually use a library. There's actually a library called Governor, I think, which you can tell it I want to rate limit it to 4 requests per second, or like 10 requests per second. So Governor. I only found out about this because he commented on one of my repositories. Yeah, so it's quite a nice high-level library. I don't think his README. The README doesn't have the code example, but it's in the documentation, and it's quite easy to use. You just say I want to have 10 requests per second max, and then you call a future, and the future will wake up when that limit is not yet reached.
Right.
Yep. And also, you can tell it rate limit. So you can divide a second into 10 chunks. So let me go every 100 milliseconds, or you can go all 10 at the start, or all 100 at the start, and then just wait till the next second. Yeah.
So the performance gain you saw from in your async version,
Mhm.
what was the
be mainly the concurrency. So if I have say 100 records, I can actually, when one record's being processed, it's going to have a web request, so that's a delay, and I can start the second one and third one, fourth one, all at, concurrently, and then so I'm waiting for the same, say 10 milliseconds with
But
overlap.
Doesn't the rate limiting somewhat destroy the gains from that?
The true rate limiting would, yes.
Okay. Oh, right.
Yeah.
So there wasn't any rate limiting
In the stub applications, no.
Oh.
In the real applications, yes.
Right.
But in the real application, if we went to the first, I think that one, yeah, I actually, oops, that's this one. I actually have this no limit up here, so when I'm testing, I actually don't limit myself. Yeah.
So you hired more cooks.
Yeah,
Essentially.
essentially, yeah. Actually, no. So I would have wanted to, but to maintain order, I can't do things in parallel, but I can do things concurrently.
Oh, okay.
Yeah. If I did things in parallel, then I could collect all of the results and then
Right. Because
chunk them.
You usually write the CSV out in the same order that it came in.
Yeah. Yeah.
Do you really?
I don't know whether that was a hard requirement, but I assume that was a requirement. And it would be,
Sort of that.
yeah. Yeah.
How you not like cooking your client's computer? Is it just the number of threads that you're using, or is there anything else that's going on?
Yeah. So I think it defaults to number of CPU cores, and even if you have more threads, if you don't have, if you have a set number of tasks which have a concurrency ordering limit, then you can't use all of your threads anyway.
Yeah.
Yeah.
But my guess is, I mean, it's quite a simple application. Even if you flood your computers, the network's gonna, or the server's gonna go slower than you can make the requests. So you're gonna have to be waiting on the server a lot more than what your computer's gonna be working.
Depends how fancy your progress bar is.
Don't have anything else and let the hardware limiting come in.
Yeah, be blocked again. IP gets blocked. Do you know how they did the IP blocking? Did they see, oh, someone's been making a lot of requests, we'll turn this off, or is it
They
an
use
automatic?
failed ban, it depends on the product.
I don't know which one it is, but I know it's automated because it auto unrun as well.
Right.
Yeah. So it would probably be a number of requests from this IP in this interval, and then you like block them for however long. Yeah.
And how often do you have to do this? How long does it take? Like 24 hours to.
So I don't have the full data set, so that was the other person has to do it.
Yeah.
And I know he left his computer on overnight.
Yeah.
But at least you can resume from where you left off, so you can do it in bits.
Okay.
Yeah.
And how often do they have to do it?
I don't know.
Okay.
Yeah. I just did the app. Yeah.
Real estate use failed ban.
Used to what?
Use failed ban on the API
Oh, okay.
side of things,
Yeah.
and you could sign up to a notification when new data was available.
Uh-huh.
Keep a track of your requests, but I don't know if they've changed that. I don't know if that was real estate use or not.
Yeah.
Yeah.
Have you tried doing any like GUI stuff with WebAssembly? Is that possible? Like fancier GUIs?
So one, I haven't done anything with WebAssembly.
Yeah.
Two, well, the short answer is no. But two, WebAssembly, I'm not sure if every browser supports threads.
Yeah. What kind of threads? Workers. Web workers.
Yeah,
Yeah, they do.
they do.
Does Rust use like green threads, or does it using actual like libraries?
Does someone know?
Um,
I think it's green threads, but
no, it uses operating system.
oh, OS threads. Okay.
There's a big long discussion.
Oh, right. They used to have green threads, but then they got rid of it.
Yeah. Yeah, there's a good talk about it, if you want to learn about it. Someone goes through the history of multi-core processing in Rust,
Yeah.
and why they're using operating systems recently. And the reason is, in a nutshell, is because every platform supports it. it's amazing to think of what what Rust goes through, like everything they think of, just to implement something. A lot of it comes down to they implement it because that's how it's done in C.
Yeah.
And because you need to be able to like interface with C, you have to kind of do a lot of the things the way C does it. If you want to remain quick, especially interfacing with C.
Do you know much about how the async await stuff looks under the covers in Rust?
I will say no. It's probably the smart answer now. Yeah.
Wait, I think you explained it a little bit. Like they've implemented something called futures, and on a future, you need a poll to see. This is at a very high level. You can probably explain it a bit more.
The async book here, it's in the links. I will put this repository online. It explains some of how futures is implemented, and most of the time you don't have to implement your own future. Well, I didn't need to implement any feature when I implemented the app, so I could use just pre-implemented features, and as well as just async blocks. Those work well enough for me. Yeah. Yeah. So read these first two books. They're really good. Yeah.
There's a video on YouTube by a guy called John. I can't pronounce his last name, but he explains how like the runtime works and how it pulls the futures. But it was done at a time before the async await sugar, so it was back when you had callbacks. So I'm not sure how relevant it is now, but
Yeah, futures is another example of where they iterated quite a few different kind of implementations of features before they kind of settled on we're going to do it this way.
And I implemented that app in like 2 weeks without knowing features at all at the beginning, so it wasn't too hard to pick up.